Okay, data representation. So now before I get to the audio and images and video, I would need to talk about numbers first. So everything that you've been doing so far with decimal, converting into binary, and hexadecimal, which is also binary, by the way. It's an easier way of representing binary. So that all that is just representing these numbers that we use on a daily basis as information, that as ways that the computer could understand. As I said, hexadecimal is just an abstraction of bits. Like, it's easier to read 2 rather than these sequence of bits. So that is representing numbers, and there are two types of numbers, like two categories of numbers: whole numbers, integers, and floats or real. Now integers, they could be like bytes and shorts, but you don't really use shorts in modern programming. And integers, normal integers, and long, which is 32 bits. So to represent this data, you want to convert the decimal to base 2. So base 10 to base 2. And you want to represent it in a way that the computers would understand. Now, for floats, it's easy for you to write 5.25, so on. But for computers, it's hard for them to have precision with these values, because it takes a lot of memory to store every single point. So they use like a smart way of representing floats, which is by storing the sign by its own, exponent on its own, and mantis on its own. So basically this whole chapter is just explaining how to store the data storage. And that's the point of learning how to convert between the bases. It's for use in this type of stuff. Now that you've now of course there are also signed and unsigned types of these, and usually computers store that as 2's complement because that's much easier to process. If you look at the table for adding to 1's complement, I think it's in the next chapter. Basically it's very hard to add 1's complement, and there's like lots of things that could go wrong. So that's integers, floats. Now we'll get to images, audio, and video. And that should be over here. Oh, first text. So computers, they don't store, like for example, if you have A, computers don't store every single bit of this A and like all the pixels of A. They just store a representation of it. So what computer scientists did back in the day is that they mapped integers, for example 1, 2, 3, etc., into a character that you could see. When you print, it converts these numbers into a character that the computer could understand, like that could be printed, and that is called ASCII. So in ASCII, it takes certain numbers, okay, to be specific, chars, which is just a byte, by the way, just a byte, usually a byte of data in ASCII. In UTF-8, it's more complicated. So in ASCII, it maps certain characters to, it maps certain numbers to characters. So that's how they represent characters. And when you put characters together, you get a string. And usually in Java, you denote a character as just one quotation, and in for strings you use double quotes, but in Python it doesn't matter. And for most characters, most English characters, it could all fit in ASCII. But for other languages, it uses UTF-8 and UTF-16 and I think 32. But these are more complicated ways of storing data. But I think UTF-8, it stores it in 8 bytes first, and if it needs to, it'll store it in more bytes. And of course, they don't store all the bytes, all the pixels, because it takes too much memory. So instead of just storing all the pixels, you just represent as a value, like 97, and then you map it into a set of pixels which could be printed, which would be A, for example. Now for, and of course ASCII, Unicode, and other codes. So of course it needs to be like a standard. If it wasn't standard, then you wouldn't be able to process it easily. So as you could see, 97 is A, and of course there's 26. So if you add 97 with 26, you get 122. Same with this, 65 plus 26 should be 90, or 25, because including A. Same with this, 25. So you probably don't need to memorize this, but if you want to memorize it, just memorize these two, capital A, small a. Now storing audio. Now when you store audio, there are two, like when you measure audio, it's stored as a wave. And waves, they don't have like discrete positions. They're continuous. That means they, like, you could zoom in and zoom in and zoom in, and you'll never get to like to an end. So also the wave is like when you have a speaker, the wave is just that plate going forward and backward. That's what the wave and the air being compressed and uncompressed. I forget the word, but basically it's stored. Audio is represented as a wave. Now, of course, the point of storing data is that you want it to be as compact as possible. So you don't want it to take too much data. And of course, this is a big problem back in the day, but nowadays we have a very large amount of storage space. But these days, but still, we want to keep the file sizes as small as possible. So what we do is first we would sample this wave at certain positions. So we would get this wave, okay, and then we would check every few milliseconds what is the value of the wave at this point in time. Now that's sampling. You're at a certain frequency, you're checking what is the value here, what is the value here, and of course it'll be like in real time, like it'll check here, what's the value, what's the value, what's the value, what's the value, and then quantization. So now the number of data points you could take, it's infinite. Okay, you could keep zooming in and you would keep finding more. So you want to make it discrete, so only a few values. And of course, the more values you take, the better quality the audio would be. So the smaller the time frame between each sample, the higher quality the sound will be. So that's sampling. Of course, you could like say sample the wave at every 10 milliseconds or something. That's sampling. Now, when you sample it, the actual it could be represented like the amplitude of the wave could be represented as volts. Let's just stick with volts, and that could be like 5.5 5, 6, 2, 8, and so on. But computers can't store this. So what we do is that we quantize it. We make it into a known quantity. So we convert 5.555, and so on. Basically, it doesn't end. And then we make it into an easier number for the computer to store. So we usually round up or round down, and like a simple example is like storing values from 1, 0 to let's say 32, and it would have a step of 1, so it would be 0, 1, 2, 3, 4. Basically, you're storing integers. So what you would do is that you would store it in a certain amount of bits. So what you do is that you would round this up or round it down to be an integer, but it doesn't need to be an integer. The more bits you take, the more accuracy you could have. So we round 5.5 so on into 6. And now we could store this value into some bits. So that's quantization. You're taking an analog. Now this is an analog wave, okay? Now we want to make it digital. That's the whole point of this. This thing that we're doing: sampling, quantization, and encoding. So after we take the bits, we round it. Now it's stored in a certain amount of bits. Now this is called the bit depth. The amount of bits that you take is called the bit depth. Then the amount of times you take the samples, if you multiply the amount of bits taken times the seconds between, times the samples per second, so the bits per sample times the samples per second, then the samples will cancel out, and then you would get bits per second. So bits per second, we call this the bit rate. So we take a certain amount of samples every second, samples per second, and that is the frequency. Then we multiply the frequency with the number of bits that each sample stores. Then we multiply it together, and then we get the bit rate. Now sound encoding. Now this is just the standard for sound encoding, MP3. I forgot encoding. Now encoding, so basically you just store these bits in like so they didn't go into depth here, but you want to store it somehow to compress it and make it small. Now here they talk about some compression. So MP3 is the standard for storing audio, and it uses 44,100 samples per second, 16 bits per sample, and it results in a bit rate of this per second, and it's compressed. So for example, if you had a line, you wouldn't store every single point over here. You would just store a representation of it, or like an easier way of representing the line. So it might be almost a straight line, but maybe it's like jagged a little, but you could approximate it. So this approximation is called lossy compression. So instead of taking a point in every, like taking lots of points, we could just take a few points or compress it somehow. And this would be lossy. If we destroy data, or like it's not perfect as it was before, then the data would be lost and it would be lossy. And now this point will come up in images. Now we can't store every single point on the line, but we could take an approximation. So raster graphics is just taking all the pixels inside the image. So you're measuring the value and then you keep measuring it across the image. But this takes a lot of memory, but sometimes it's necessary. So this is also called bitmap because it's literally a map of bits. Of course, you need to take it in rows and columns. It's called scanning, and of course it also has color, but we're going to get to that in a minute. Sampling in this case is normally called scanning. So I think like it goes like that through the image, and every significant part is called a pixel. Now there's something called resolution, or like pixels per space in the image, and the higher the resolution, the more bits it would take, of course, because it takes more bits per linear inch. And of course we're taking an approximation, but usually this approximation is quite good because the resolution is too big for you to make out the pixels. If you look close, you'll see the pixels. Now the color depth. Now there are two types of colors. Now usually you store colors as hexadecimal RGB. So there's hexadecimal there's a bit for red, a bit for green, a bit for blue. Say this is AA, this is 00. So this is 1 byte. I said bit before, but byte. So 2 hexadecimal is 1 byte. As I said in the beginning, hexadecimal is just an abstraction for bytes. It makes it easier to work with bytes. So if you store it in this way, if you ever wrote CSS, you probably saw this before. Now this is just 1 byte for red, 1 byte for green, 1 byte for blue. So this is called true color. So we take 24 bits. 24 bits is just 3 bytes. Each byte is 8 bits, so 24. And this would be true color, so we could barely see the difference between this and true color. And now index color, we're just now there's where did it say? But did it say? So basically 24 bits, there are lots of color possibilities of colors. So instead of taking all those colors, we could just take a small portion of them. So we would take one part from here, here. So instead of storing 24 bits, we could store maybe like 8 bits. Okay, and that would reduce the bits per pixel. Because now every pixel I'll get to that later, but usually in a bitmap image, so a map of bits, you take every pixel would have its own RGB value. Of course, 24 bits per pixel, that's a lot. So some methods use indexed color, or some methods use real color, but they're compressed somehow. So JPEG and GIF. Now, as we said before, there are two main types of color. True color, which is storing 1 byte for each color, and index color, which is taking only a part of the whole. So JPEG does some smart techniques to reduce the number of pixels need to be stored, compressed, but of course maybe it's lossy compression, so maybe the quality of the picture wouldn't be as good as if it wasn't compressed. And so this uses true colors, but it's not as simple as just a normal bitmap image. So bitmap image is just a group of bits, a map of bits, like a 2D array of bits. But a JPEG, it uses encryption. I think like it has something to do with waves to approximate the pixels. So it uses true colors. JPEG uses true colors, but it compresses it. Now GIF reduces the colors used and uses indexed color to reduce the number of bytes per pixel down from 24 to a lesser amount. It doesn't specify here. Now I said before, instead of trying to see every single pixel inside this line, you could just approximate the line. Like, even if it wasn't a straight line, you could just approximate the line. So usually this comes in the form of an SVG, solid vector graphic, or something along those lines. But basically you're approximating. Instead of taking every pixel, you're just saying this is a line, this is how long the line is, and this is the color of the line. So of course that would take very little data to store, and that's what they call vector graphics. So vector graphics, you just take some known parameters, like a circle has a radius, of course, and the location of the center point, x, y, and the color, the fill style. And so instead of taking each pixel in the circle, you could just take an approximation. So you store the radius, the center point, and then that would be enough for you to recreate the circle somewhere else. And now the special property of a vector graphics is that if you zoom in, like here in OneNote, it uses vector graphics to write stuff with. So if you zoom in, you wouldn't be able to see the pixels, because it's just like it's a mathematical formula to calculate the pixels. But if you use JPEG or GIF, when you zoom in, you start seeing the pixels. But with vector graphics, when the more you zoom, you wouldn't be able to see pixels. So as you might have seen that, but it was pixely at start. Then you zoom in, after a few seconds, it started becoming more clear. Now I'll show you an example of an SVG, a vector graphic. For example, in Twitter, or almost every website, they use vector graphics to store these images over here. So if we inspect this, you will see that it is just an SVG, and this is all the data for the SVG. No need to store every single pixel on here. You could just store an approximation. The same thing with here. You know that this thing is just a box that has curved edges, and it has two lines over here. Of course it's probably more complicated than that, but you don't need to know it for this. Now storing video. Now as you learned over here, JPEG is just one image. So what video does is that it takes one image, and then it takes another image, and then it moves across the images, okay, in a certain frame rate. Now, as you learned here, every pixel takes 24 bytes, so it's very inefficient to store like a 1024 by 780 or something, and then store every single pixel of that. So what they do is that they store, so in the beginning they have a bunch of images called frames. Now instead of storing every single frame, they compress it. So instead of storing every single frame, they take a few keyframes, and then the frames in between, they only have the changes inside between each frame. So this frame has changed in the time between these two frames. This is what changed, and then over here, this is what changed, and then it'll hit the keyframe which has better which has all the data that the image needs. And sometimes the keyframe is missing. So when the keyframe is missing, you probably see like artifacts in the video, and that's when the keyframe is missing. So yeah, that is data storage.